Hello everyone, today we will be going over stacks today, and without any further hesitation, let's get started. And now let's go over the second part for our practice problem, developing a stack using a linked list. So to be able to get things started, we always include our libraries that we always need just based on general principle. So include a stream, and then we will be using namespace std. I'll have a class called stack. And what we'll be doing, since linked lists are made of nodes in particular, and the benefit of linked lists are that they can be added dynamically, so we don't need a fixed amount compared to an array, and this provides greater flexibility as well, while keeping an efficient space and time complexity. So we'll have a struct stack node, which will be called entirely inside of our class. I'm going to have int data, and then we're going to have stack node next. This is how we construct nodes inside of our linked list. And we will initialize a top. So stack node is going to have a top node as well, since stacks are comprised of or structured like a series of plates, last in, first out. Now, all right, I will be creating a public instance. And then we're going to initialize our function that we have for top null pointer. That's how we just initialize inside for linked lists. And then we're going to put our function push pop peak and is empty. And I'll just put this here to make sure it just stays quiet. So to push, I'm going to have a function called void push int x. And then we're going to initialize our first node, so stack node here, new node is equal to new stack node right here. And then if the new node is not there, hence the exclamation point, we will be outputting a heap overflow. No nodes detected. Always have an edge case. We always start with our edge case. Return there. And then what we will be doing is that we're going to be linking up every piece of data with our new node. So new node data that we can use. We can even call this next as well, just to make things better. Or actually data. Yeah, that's better. It's actually going to be calling upon just a raw data point over here, equal x, the new node to the next one, which will be referring to, because we're putting in our data inside, and referring that as x. And finally, we're going to put this one as the top, and then we will re-declare as new node for top. So that way we're still stacking on each other. And now we will be focusing on the pop. Now we can do the same thing we did before by using an integer function as well. And for peak, I'm just going to do the same thing that we did before. In peak, then is empty, bool is empty, to be able to fill out everything else. So pop, we have here if there's nothing at the top, then we have a stack underflow. Nothing at the top, we'll return -1. And this is what we will be doing. We'll be doing this technique called the swap. So we're going to have a stack node temp equal top, and then top is going to be equal to top to the next node that we have that we're referring to. That is just considered a placeholder in that case whenever we are putting in more data. And I'm going to have another integer called the actual popped element. Popped temp data. And then finally we're going to have this function that is already called within C++ called delete, and we'll delete this temporary node that we made to be able to use it as a placeholder, and then we're going to return our popped. So what it's doing is that it's actually getting the data from our temporary node that we have. And inside of our temporary node that we have made, that we are scanning throughout the rest of our entire linked list. Hold on, give me a second. Oh, there we go. No equal sign right here. Yeah, it's just complaining because there's nothing right there. Okay, there we go, that makes sense. So it's really getting the exact data point inside of the temporary node we have made. And since we are scanning throughout our linked list, because linked lists are comprised of a head and then a series of nodes as well, especially if we're using a singly linked list at the same time, which is the most conventional way that a lot of linked lists have been developed. So this is just one direction that we can do. You can develop a stack with a doubly linked list, but for the sake of convenience, we're just focusing on a singly linked list in this case. And then I'm going to be focusing on peak. So if there's nothing at the top, we can say that stack is empty. Oh, and then we return -1, not 0 in this case, because we're dealing with linked lists. So totally different. So linked lists use functions, and arrays like to use booleans and integer functions as well. Then we will return the top data as well, because the top data is looking at the specific element inside of our top component for our stack. Then we will, this function for boolean will be pretty simple. We will have return top equal null pointer. It's indicating if it's true as well. And for the sake of everything, I'm just going to create another function to print out our stack of linked list nodes. So that means in particular, I'm just going to call it void print list as well, much like what we did in the linked list video as well. So print list, what we will be doing if is empty. In this case, as an edge case, we always think about edge cases first. Count stack is empty, and we end it, and we just simply return. And then we'll have a temporary node as well, indicated as the top. And because what we do for linked lists in general, we always print directly from the head and the rest of the nodes, this explains its efficient space complexity, while temp doesn't equal a null pointer, meaning that there is something there. We're going to output temp data, and then temp is equal to temp next. Finally, we will be outputting everything until the very end of our list, depending on the context of what we have. So I'm just going to call this printing out our list. Okay, there we go. So push, pop, peek, checking if it is empty, and having a function right here to print out and check for everything as well. Now, let's go over to our main function, and what we are going to be doing, we always initialize or call upon our function, call upon our class and declare. Then I'm going to push, and I'm going to pop, peek, then print out everything. So that means we're going to have stack right here. I'm going to call the stack. Then push. I'm going to have stack.push, element of 10. We'll do the same thing we did before. Now notice, in arrays, we always need a fixed size, but linked lists are very efficient because you don't need to have a fixed size, and you can add them dynamically. So right here, this is how we push. Then I'm going to pop something from the stack. So popped 30 from the stack. There we go. Then peak. Is our top element. And then end that. And then we're going to print out everything. Our updated stack. Oh, sorry, print list. There we go, that's better. Return 0. Let's just build everything and make sure it's good. All right, build succeeded. And let's run this bad boy. There we go. Yep. All right. So we have main, print list, which displays everything, checks to see if the stack is empty, checks the peak of the stack, pops it, and then pushes each new element accordingly into our stack. And looks like it did pretty well because it goes last in, first out. We push each element accordingly, 30, 20, 10. And we have already done our necessary functions. So let me just zoom out here, be able to help you folks see. And I'm also going to have this in the description as well, or actually the comment section. Yeah, there we go. So feel free to take a few screenshots of this as well. And yes, so this was stacks over here. Hey everyone, thank you again for taking time to watch this video. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.